Hey, this is Mr. Aiden. This is AP Chemistry. This is the 2018 AP Chem exam. Free response problem number 3. My son Tanner tells me to stop doing videos and play. What do you want me to play, Tanner? Call of Duty Modern Warfare. But I don't know. I think the shaking of the screen kind of makes me sick. So I'm just going to keep doing videos. And let's take a look at AP exam. Problem number 3. So here we go. Problem number 3 starts with we have two ions. We have Fe plus 2 and Fe plus 3. Iron plus 2 and iron plus 3. And you can see the first thing they want me to do is to find the ground state electron configuration of the Fe plus 2. Keep in mind, they don't want me to find the Fe solid. They want me to find the ion Fe plus 2, which means that iron has lost 2 electrons. So we take a look at where the iron is on our periodic table. And when he loses 2 electrons, it's going to lose 2 electrons from that S subshell. So we want the full electron configuration. So I'm going to do 1s2, 2s2, 2p6, 3s2, 3p6, and remember the 4s2 is gone. And so what do we end with is 3d6, and as Timmy says, woo! Good. The second question, so that is problem A. A is worth 1 point, of course, okay, to find the electron configuration of the iron plus 2. You can see where most students mess up on that one is where they forget that what they're looking for is the ion and not the solid. B says the radii of the ions are given in the table above, and you can see iron plus 2 has a larger radius than iron plus 3, and they want to know why does iron plus 2 have a larger radius than iron plus 3. And well, keep in mind, we first always want to go to our nuclear charge. The nuclear charge, or the number of protons, is going to be the same for the iron plus 2 and the iron plus 3. So it is not having anything to do with the nuclear charge. What's happening is the electron shielding, or electron to electron repulsion. Electron to electron repulsion. So you can see the electron to electron repulsion is greater for the iron plus 2 because it has more electrons, and therefore the radius, the ionic radius, will be larger. Okay, and so that is worth, obviously, that's worth 1 point for giving that discussion of the electron-electron repulsion, making that ionic radius larger. Then C is going to talking about Coulomb's law, and we're seeing how iron plus 3, those ions are going to react with the water molecules. Remember, we call that ion to dipole interactions, right? Ion to dipole interactions. And why would iron plus 3 interact at a greater extent with that water molecule? And it's because the ionic charge is greater. Remember, Coulomb's law deals with two things. Remember, the force of Coulomb's law is dealing with that Q over R squared. So it deals with the charge and the radius. And so you can actually talk about this in terms of radius. With the smaller size of the iron plus 3, it's going to have a greater attraction. You have to either talk about the ionic charge being greater or the ionic radius being smaller, and that gives the ion to dipole attractions a greater extent. And that is going to be worth 1 point for a valid response right there, a valid explanation. Let's take a look at, as we go along, to problem D. So problem D, we're starting to go into what's called a titration. Now remember, this titration is the titration we did in class, and this titration is the iron plus 2 with the permanganate and in an acidic solution, that H plus solution, and you can see that color is going to change. We have an endpoint, and the endpoint is a color change. That's when we knew that color change. Remember, that color changed to pink, right? And so we want the balance reaction for the half reaction of, we want the iron plus 2 becoming iron plus 3. So you can see the atoms are equal, but the charges are not equal, so I have to add 1 electron, and that is my half reaction. That's worth 1 point. Okay? And then we go into our titration within E. E, we cannot use M1V1 equals M2V2. Why not? Because it's not a 1-to-1 ratio. Remember, this is something we've talked about before. And so we are going to take the molarity of the KMnO3, the 0.0350 molar of the KMnO3. We're going to multiply by the number of liters we use of that KMnO3, which is 0.01748 liters. And that gives us the number of moles. That is going to give us 0.000612 moles. And who's that moles of? That's moles of your potassium permanganate, the KMnO4 minus. We then need to do a molar ratio between the KMnO4 minus and the Fe plus 2, because that's what we're trying to figure out. Keep in mind there's 1 mole of permanganate for every 5 moles of the Fe plus 2. So we need to take this value and we need to multiply it by 5, which ends up giving me 0.003059 moles of the Fe plus 2. What do we do then with moles? In order to find molarity, we're going to take that 0.003059 moles of the Fe plus 2, and I'm going to divide that by the number of liters of the Fe plus 2, which is 0.010 liters. Okay, and that will give me my concentration of 0.306 molar of Fe plus 2. And so that is, there's actually 2 points in this problem, obviously, because you're definitely going to be doing a lot of work here. You get 1 point for finding the moles of the potassium permanganate, and then 1 point for the final molarity here. Take a look at F here. F is saying, explain why the volumetric flask is a poor choice. Why would a volumetric flask be a poor choice for delivering a volume? Well, remember, a volumetric flask has one job in life. A 25 ml volumetric flask has one job, that's to deliver exactly 25.00 milliliters. It is too precise, which means we cannot deliver 17.48 milliliters. We would need a graduated cylinder or a burette or something. That 25 milliliter volumetric flask is way too precise, and so that is going to be worth 1 point for a valid explanation of why that is a really poor choice. Okay, let's try to finish out this problem here. Sorry, we're going to come back. We're going to try to finish out this problem here, and you can see now we have a separate experiment. And we have a mass of iron with an inert impurity of 6.724 grams. We cannot do anything with that number because that is not pure iron. That is iron plus an impurity. So we're always going to take that thing with an element plus an impurity. We're going to put it to the side for a second. But we do know for G, we do know 7.531 grams of iron oxide, Fe2O3. And so what do we always do with the mass is we divide by the molar mass. The molar mass is 159.70 grams per mole of iron oxide, and that gives me 0.04716 moles of, you got it, Timmy, iron oxide. Timmy's doing this problem with us. So, but that's not what we wanted to know. We want to know the moles of the iron. So keep in mind, for every 1 mole of Fe2O3, how many Fe's do we have in Fe2O3? We have 2 moles of iron in there, which means we're going to have to double this number. We're going to have to double this number, and we end up getting 0.09431 moles of iron. You got it, Tim. And let's go to H. A is now asking us for the mass percent. Any kind of percentage is part over whole. okay, part over whole, which means we know the whole amount is going to be the 6.724 grams of the iron and the impurity. But we want to find out the part on the numerator. How do we figure out the part? Well, we have to take the moles of iron, these 0.09431 moles of iron, and we need to multiply by his molar mass, which is 55.85 grams per mole. And that ends up giving me 5.267 grams of iron. This is my part. You can see this sample has iron and an impurity of 6.724, but we know that there's only 5.267 grams of iron in there. There's only a small amount of iron in there. Actually, it's pretty large. And obviously, what do I always do? I multiply by 100%, and that gives me my percentage, which is 78.33% of iron in that sample. I forgot to give you the points for G. There's only 1 point for G, which is finding the number of moles. Okay. H is actually going to be 1 point is earned for the calculation of the mass percent. So we get 1 point for the calculation of the mass percent. Now we have one last part of this problem. It says if the oxidation of iron solid in the original sample was incomplete, so that some of the 7.531 grams of the product was FeO solid instead of Fe2O3 solid, would the calculated mass percent of iron be higher, lower, or the same? And we know that just thinking about it logically is the calculated mass of percent, the calculated mass percent of iron is going to be lower. Why is it going to be lower than the actual mass percent? It's that sample is going to contain some FeO. That sample is going to contain some Fe2O3. So if it's containing some FeO and it's containing some Fe2O3, think about it. The calculated number of moles of Fe is going to be lower, which means the calculated mass percent will be lower as well. So when the moles of iron are calculated, we assume that there was all Fe2O3. The calculated moles of Fe would be lower. So if the moles of Fe are going to be lower, then the mass percent of the Fe will be lower as well. And so remember, when you work through a problem like that, just go step by step in the calculation you just did. That was worth 1 point as well. So let's review our points for this problem. You can see A was worth 1 point for the electron configuration. B was worth 1 point. C was worth another point. D was worth another point. E was worth 2 points. That gives us 5 and 6 points. F is worth the 7th point. G is worth the 8th point. H is worth the 9th point. I is worth the 10th point. And that is all 10 points. Make sure you go to MrAiden.com. Timmy's cheering. This problem is done. So we'll catch you on the flip side, homies. On the flippity flop. And I'll catch you later. Bye-bye. Make sure you put in your results on MrAiden.com, yo. All right.